Thank you, Paige, and good day, everybody. I hope you've enjoyed the conference so far. My name is Lalit. I'm the CTO of GridGain Systems. For those who are new to Apache Ignite, welcome to the Ignite family. For context, Apache Ignite was formed about 10 years ago when GridGain donated its application code base to the Apache Software Foundation. I'm very excited to be here today. After all, these are exciting times to be in the business of data processing. There has been an explosion in AI and AI-related technologies. There has been exponential growth in both the hardware and software related to AI. New unicorns have formed related to AI in AI companies. And there has been a variety of use cases and applications that we've seen with AI lately, especially in the last couple of years. So what are these use cases? Well, these use cases span the spectrum of AI. We've seen use cases around Gen AI with code creation and content generation and content creation to conversational AI related use cases with chatbots and use cases with customer engagement to predictive AI related use cases, whether it's around fraud detection, whether it's around failure detection and failure modeling to forecasting and so on. But none of these use cases really even scratch the surface of what AI can do for us and where AI is heading. Let's take a look at these pictures. I got these pictures from the Guinness Book of World Records website. These are pictures of the celebration at the National Day in China from last year, so about October last year or so. What they did there was they actually used drones instead of real fireworks as part of their celebration, and in the process broke the world record for the most number of drones that were used simultaneously in the production of a single exhibition. The way these drones were programmed basically were all of these drones were pre-programmed with a predetermined flight path and the associated lighting, and then they were set off and they kind of went into the sky and created this three-dimensional formation and went through the whole process with that formation through that predetermined path. Now, while this was impressive, you had 10,000 drones being managed by a single computer, impressive enough to actually make it to the Guinness Book of World Records. There's nothing to do with AI in this. So why am I talking about this? Why am I bringing this into this conversation, bringing this example? What we'll do is let's see if we can extend this example a little bit and see if we could do something like this a little differently. Imagine that these drones were self-programming and they could dynamically program what they needed to be done for the desired outcome with something like Gen AI based technology. So what you do is you could, let's say, create a three-dimensional shape, a model on a computer, and then have that three-dimensional model be made available to these drones. These drones then, knowing the model and knowing what other drones exist in that ecosystem, in that situation, they then self-program all of them to be able to create these shapes dynamically in real time and position themselves appropriately in the context of that picture against and vis-a-vis all other drones. And they talk to each other and they communicate with each other so that if a drone goes bad, it malfunctions, the other drones take up that position. That drone gets eliminated, the other drones take the position. If there's wind that is blowing a certain gust of wind and that is shifting the shape, drones are able to self-adjust. They are able to adjust the thrust in the appropriate direction and reattain the desired shape that they wanted. What this is doing really is basically what we're saying here is that we get to a state where these machines self-program and self-govern and adjust according to the desired outcome. Basically, we are combining Gen AI with conversational AI, although there's not a whole lot of conversational AI here, but we are combining Gen AI, conversational AI, and predictive AI to achieve the desired outcome. And if you put it all together, these bots that are self-governed, self-managing, self-programming, self-learning, this sounds a lot like being human. And if that sounds familiar, I'm not very surprised because we have seen little subliminal signals of something like this coming in movies over the years. The idea here is basically that you have machines, self-governing, self-programming machines, autonomous machines that can interact and communicate with each other to achieve the desired results. Um, and for those who have sat in autonomous vehicles and autonomous taxis, you see them, going on the streets of San Francisco all the time. That's kind of exactly what we're talking about. These cars are at any given time processing what's happening around them in the surroundings in traffic, analyzing it, and reprogramming themselves to be able to basically get to that outcome, which is taking the passenger from point A to point B safely, following the traffic rules and so on. Um, so what they do is, and in fact, sorry, um, what will happen is for these cars to be even safer and to ensure that they can run smoothly and successfully without accidents. An ideal situation would be where these cars are talking to each other, and are in this peer-to-peer network where they communicate with each other. They are self-governing. They manage the situation by themselves, absorb events from their surroundings, whether it's traffic lights, whether it's pedestrians or whatever, react to it and behave in a way that is very well coordinated. And that's when you'll achieve that situation where technology like this can also be safe to a point where they can do the simplest of things, like maybe diagnosing and repairing an automobile, to something a lot more complex, like maybe able to perform surgery and then react to the situation in the surgery. Now, let's take a look at what do you need to be able to make this happen. If you crystallize this down to something very basic, very fundamental, what you're talking about is basically autonomous, self-governing, self-programming AI agents with their ability to assess and analyze what's happening in their context, in their environment, in terms of events and situations that are happening. So these AI agents being able to react to events and situations in their environment, when put together, get to that point where you can have this kind of a self-governing autonomous machine-to-machine interaction. But there is still one thing missing here, and that is historical context. Um, Along with events and along with the environment and the situation around these self-governing, self-programming agents, you also need historical context. So when you put these three things together, basically what you're looking at is what you need for the desired goal to be achieved with AI, the desired promise of AI as such. You need all of the relevant information. You need all of it in real time. You need the ability to process all of this information immediately in real time. And what do I mean by relevant? Why relevant? Let me give you an example. Let's say you execute a trade to buy some stock of NVIDIA. In isolation, there is not much to this event. You bought some NVIDIA shares, so what? But when you put it in the context, and before you put it in the context, NVIDIA is also one of those high growth shares with high beta, high volatility or whatever. So when you put this particular trade execution in the context of a portfolio that has a certain risk profile, and by buying a high beta stock, adding it to your portfolio, you could potentially change the risk profile of your portfolio. And then to bring that risk profile back to the desired state, you have to then execute a balancing trade on the other side, of a very low risk, low beta trade. So you can then have an equilibrium effect on your portfolio. So an event in isolation may not mean anything, but that event in the context of the bigger outcome, when applied, when you put in the information of what else do you have in your portfolio, what is the risk profile of each of those assets in your portfolio, what is the collective risk profile with those assets, with that historical context, the processing of that event is very different, and you behave very differently when you put that context around that event. So that's kind of what I mean by relevant. Now let's shift gears a little bit and let's actually dig into what the underlying technology architecture for something like this would look like. So what you have is basically you have your events and your historical data. What you have to do now is you have to process these events to a point where you analyze your event, You determine what historical context you need. You pull in that historical context. Maybe you do have your agents do other things, or you're doing something as simple as feature extraction, generating vector embeddings. You're writing that down to your AI data store, and then you're executing your AI model against that AI data store to be able to draw your inferences. So this is what a typical classic, very basic AI ecosystem would look like. Your events, your historical context, your processing engine that can help you process these events and draw your inferences. Now, across this entire ecosystem, there is a lot of inefficiencies. So for somebody who has to be able to make a decision in real time, especially in the context of a vehicle, an autonomous car that's driving on the streets of a city, where it has to react to pedestrians, it has to react to traffic lights, and whatever else is happening in the traffic around it, or when you're performing surgery and you need to be able to understand the patient's history and some context around the health condition of the patient and certain things that can and cannot be done, etc. You have to be able to make decisions quickly, and you cannot afford to have any latency between an event happening in that situation and a decision that has to be made after having to reprogram yourself and so on. So, what latencies do you see here? A couple of big ones. One is every time you see that little red dot moving, you're basically seeing data cross an application boundary or an application silo. And every time it crosses an application boundary, you're introducing network latency. The other latency here is basically in data retrieval and data storage. So every time you read and write data, every time your model is querying your data store to pull historical data to be able to execute and draw inferences, you are introducing disk I/O based latency. So you have those two primary latencies in this ecosystem. Let's see how we can make this architecture a little bit more efficient. Let's start with perhaps adding a data hub. What this data hub does is it allows your processing layer to access all your historical context and relevant information through that single location, through that single store, that data hub. So it does not have to worry about all of these different data sources that are across the data ecosystem, all of the different data formats, data types, etc. It can just go to the data hub and pull that information. So you now have a little bit more efficiency in terms of being able to retrieve contextual data. You still have that network latency and you still have the disk I/O related latency as well. How about if we put all of that processing components, all of these agents that are talking to each other, that are communicating with each other, that are handshaking with each other in the context of a bigger workflow to be in a distributed in-memory compute grid. What that allows you to do is it allows you to have these agents talk to each other a lot more efficiently, and it allows you to also scale that compute layer horizontally as needed, depending on the workload intensity or spike in volumes or events or whatever that you have to process. So you've added a little bit more efficiency into the system, but the network and the disk I/O latency still exist. So let's see what we can do here. Let's say we put that data hub on a low latency data cache backed by some durable asset compliance store, allowing you to now scale the data that you needed both in memory and on disk. What that does for you here, more importantly, is it is by putting that data in memory, you are eliminating that disk-based I/O. So you have now successfully eliminated one big latency in this whole architecture by introducing that in-memory cache for your data store. But you still have the latencies we talked about around the network between these different layers and so on. And more importantly, you have that latency around inferencing, where you're either whether you're training your model or whether you're executing a model to draw inferences, because both training and model execution take large amounts of data, and reading large amounts of data, even though it's in memory, but moving it over the network to that compute layer is time consuming. So what you could do here is you could at least, if not eliminate all latencies, all network latencies, all network hops, at least minimize them. Now, events are being generated, are being formed, are being created across the globe, across your data, data value chain, data ecosystem. So to say that there will be no latency between your events and your processing layer basically is not necessarily easily possible. But what you could do instead is you could at least eliminate that latency between your compute layer and your storage layer by putting both of them into a single platform, and thus taking away that one big hotspot of model execution, model training, and inferencing, so that that one component or that one part of our whole AI process becomes a lot more efficient. And by doing this, you are eliminating that movement of data over the network. You are allowing the execution of decisions to happen a lot faster with your events and with that historical context. And that's what you achieve with this architecture. Now, for those who have been using Ignite for some time and who have implemented applications and use cases with Ignite, you will find this architecture very familiar because this is exactly what Apache Ignite does. Apache Ignite is that foundational technology for data processing where you have to execute those AI workloads at low latencies and high speeds and so on. And what we have to do now as the users and the custodians of Apache Ignite, it is our opportunity now in this age of AI and also our responsibility to ensure that the promise of Apache Ignite is fulfilled, that Apache Ignite can actually be that foundational technology successfully in this age of AI. And how do we do that? We can do that in a number of different ways. I urge all of you to contribute back to the community, whether it's blogs or articles, whether it's utilities and sample codes, accelerators, etc., or even just helping us test and debug and then contribute to fixing those bugs that we discover would be of great help. And especially now when Ignite 3 has just come out, it's new. We have done a lot of testing before it was released, but we could really use a lot more eyes on it and a lot more testing on the platform with with all sorts of use cases and so on. Next, we could collaborate with each other a lot better and a lot more, whether it's around solutioning with Apache Ignite or whether it's around coming up with creative use cases and creative ways to use Ignite to address these novel use cases. And finally, sharing our experiences, sharing our success stories, sharing the challenges we ran into when using Ignite, what has worked and what has not worked, etc., with each other. So new users who are onboarding onto Ignite, who are starting to explore Ignite and start to use Ignite, can learn from our experiences as opposed to fumbling along the way by themselves and learning on the best way to use Ignite the hard way. So that's something all of us as a community can do to ensure that Apache Ignite community is healthy and thriving. And GridGain, for that matter, has done something additional to what we have been doing in terms of supporting Ignite. What we have done is we have brought on board somebody to run developer relations, somebody to engage with the developer community, understand what your experiences are, what is working, what is not working, give that feedback into GridGain, and have GridGain be able to contribute back to the community in terms of making it easier for developers to use the product to eliminate friction in their use of the technology. Michael Eliatti is a 20+ year veteran in the industry, and in the past has successfully led a developer relations program, engaging with developers, working with the developer community in ensuring that their experience in using the technology, in getting started with the technology is a pleasant and a successful one. And what I encourage all of you to do today and going forward is to connect with him, to reach out to him, and to share with him your experiences and your challenges so that we can collectively then make the community stronger and Apache Ignite a stronger product. Finally, I would like to thank other speakers who have chosen to take time to contribute their experiences with Apache Ignite with the rest of the community. And also, I also thank the people working behind the scenes to make this event successful in coordinating and running this event and so on. So thank you very much to everybody who's been working behind the scenes for this event. And with that, thank you all for listening. You have a wonderful rest of your day. Enjoy the rest of your conference. I hear that there are a couple of very interesting sessions still to come, and I look forward to hearing back from you. And with that, I will hand it over back to Paige. Thank you.